So today we are going to start with Gauss's divergence theorem. It is the last generalization of the second fundamental theorem of calculus which we are going to do. So far we have done Green's theorem, which talks about a plane region bounded by a curve, and then we have seen that certain double integral comes down to the line integral on the boundary. That was Green's theorem. Then we have looked at one more generalization of that when it was not a plane region, it was a curved region, and then the generalization was the Stokes theorem, that the double integral over the surface comes down to a line integral on the boundary of that region. Now this time what we are going to deal with is the connection between triple integral and the surface integral. Okay, so the situation is something like this. What we are going to do, so let me look at the solid sphere. Okay, and what we are going to do is I will have certain functions whose triple integral over this solid sphere, which makes sense because solid sphere is a three-dimensional object. The triple integral of certain function on the solid sphere will turn out to be the surface integral of some other function, where the surface in question is the boundary of the solid sphere, that is the usual sphere. So that is a generalization of Green's theorem again. But first let us see how do we generalize Green's theorem in this direction for triple integrals. So let me write down the statement of Green's theorem again. So the statement was double integral over d del n del x minus del m del y. This, if I do the double integration with respect to dx dy, it turns out to be integral over some boundary curve with proper orientation, and then we called it m dx plus n dy. Now we can recall that this last integral can also be written in the tangential form, that is c f dot t dt, where t is the unit tangent to the curve c. So if ct is xt yt, then tt is a constant multiple of x prime ti plus y prime tj. Okay, let us assume that this is unit tangent. If that is the case, then I can see that nt, that is equals to y prime ti minus x prime tj, is certainly unit normal, because if I look at the dot product of tt and nt, I get 0. So nt is orthogonal to the tangent, so it is the normal. Now let us look at this integral, integral over c f dot n dt. Instead of f dot t dt, I look at f dot n dt. So what does this mean actually? It means integral over c m dy minus n dx. Recall that integral over c f dot t dt, by that I meant integral over c if m is equals to mi plus nj, then f dot t was m dx plus n dy. Okay, so with that notation, integral over c f dot n dt turns out to be m dy minus n dx. Now can I write this as a double integral? So this quantity here I want to write as double integral. So given all the nice properties of the function m, n and c, I can think about applying Green's theorem in this setup. Okay, So in the usual statement of Green's theorem, what I have is that integral over C P dx plus Q dy, that is double integral over D del Q del x minus del P del y dx dy. This is the situation. Now if I compare this side with this, then I get what exactly is P and what is Q. So I get that P is actually equals to minus n and Q equals to m. So this is Green's theorem. Okay. Now if I apply Green's theorem with P equals to minus n and Q equals to m, what I get is that integral over C m dy minus n dx, that is double integral over D. So first I have to write del Q del x, but Q is m, so I get del m del x, then minus del P del y, but P is minus n, so it is minus of del n del y, okay, times dx dy. This is by Green's theorem. Now this quantity is nothing but, if I simplify, multiplying with the minus, I get del m del x plus del n del y dx dy, where fxy equals to mxyi plus nxyj. Okay. Now if I look at this integrand, this is then nothing but grad dot f by my definition, because grad dot f is nothing but del m del x plus del n del y. To remember it, it is just this del del x del del y dot mn. Okay. So this is the quantity I get. Now this is known as divergence of f. We call it dvf. So then what actually we got, if I look at the previous expression, that I started with f dot n dt, this is the quantity here, that is turning out to be double integral over d divergence f dx dy. So this is integral over c f dot n dt. Okay. So this is called the normal form of Green's theorem. It is actually this form which we want to generalize to higher dimensions. So that is divergence theorem. So what I will do is, I will just state divergence theorem for you. Then for a particular example, I will verify the theorem. I will not go into the proof of divergence theorem because it is long and it will take our time. And then we will show some applications of divergence theorem, that certain integrals becomes much easier to calculate if we use divergence theorem. So what exactly is the statement of divergence theorem? So let us go to that. So let D be a closed and bounded region in R3 which is bounded by a smooth surface S. Let F be a vector field, so it is given by f x y z is equals to L x y z I plus M x y z j plus N x y z k. Okay. Now, if N stands for the outward unit normal vector, then triple integral over D divergence f dv, that is the three-dimensional integral over the region D. So, actually what we would mean is divergence f at xyz dx dy dz. Okay. So, I can write it in this form. Usually we don't write it in the form of xyz, because if I do that, then I have to tell you what is the variation of the parameters xyz, but this is just for understanding that whose function this divergence f is and what is the area of integration. The area of integration is dx dy dz. That turns out to be double integral over S. Actually integral over S is technically correct, but I want to say that it would be an integration of functions which has two parameters. That's why this double integration comes in. It is f dot n of this function with respect to the surface area d sigma. Okay. So, this is the statement. It is exactly analogous to the normal form of Green's theorem. So, divergence f given a function f, I can calculate the divergence f of that function, integrate that function with respect to the parameters x, y, z. The resulting integral is same as the integral of the function f dot n with respect to the area of the surface d sigma on the boundary surface S. That is what divergence theorem says. So, to understand it in a better way, well, there are certain technical conditions involved which you will certainly need for existence of all these integrals. So, what we usually use is here that Lmn has the following property, that Lmn has continuous partial derivatives. Okay. So, those kind of functions we are choosing. Now, let us go to an example where we can verify Green's theorem that this really true without going into the proof of it. So, I will start with some simple example. So, let us say D be the region bounded by the hemisphere x square plus y square plus z minus 1 whole square equals to 9, and the plane z equals to 1. Okay. So, we want to verify the divergence theorem for some particular vector field f, which I am going to now define. So, f of x y z, that is equals to xi plus yj plus z minus 1 k. Okay. So, to understand the scenario, let me just draw the picture. This is the z axis, x axis, y axis. This is, let us say, the height z equals to 1. Okay, this is the projection of that region here. So my region is this hemisphere and this surface z equals to 1. So this is the plane z equals to 1, which is intersecting the hemisphere. So this height anyway we know is 4 because the radius of the sphere is 3, and this is z equals to 1. Okay, and this is the plane z equals to 1, that is what I mean. And this is the given function f. Now LMN certainly satisfies all the conditions of being continuous and having continuous partial derivatives. So all I do is first I calculate divergence f. So what is divergence of f? So that is, I know it is del del x, del del y, del del z dot x, y, z minus 1. If I calculate this, I get 1 plus 1 plus 1, 3. So we are lucky here that divergent f becomes a constant function. So all I have to do now is triple integral over d 3 dv, but 3 being a constant comes out, all I am led with is integral over d dv, that is the volume of the hemisphere given by the equation x square plus y square plus z minus 1 whole square equals to 9 and cut by the plane z equals to 1. That is actually passing through the center for this sphere. So I know the volume of the sphere of radius r, that is 4 by 3 pi r cube, and this is the half of that chap. So the volume is also half. So this is 3 times, instead of 4 by 3 I will have 2 by 3 pi, then the radius cube. What is the radius? Radius is anyway 3. So 3 cube. Okay. So what I get is 27 into 2, that is 54 pi. That is one side. Now I have to look at the other side. I have to calculate for that first the outward unit normal vector n. Now since my surface is given as level surface of a function, I know that n is grad g by norm g, norm grad g. What is g? Well, g of x, y, z is x square plus y square plus z square, z minus 1 whole square minus 1. Then grad g is a vector. That vector is given by 2x, 2y, 2 times z minus 1, right? Then what is grad g by norm grad g? That would be 2x, 2y, 2z minus 1 divided by norm of this vector, that is square root of 4x square plus 4y square plus 4z minus 1 whole square. So I can take 2 out, I get x, y, z minus 1 divided by but xyz is a point on the surface, and I know x square plus y square plus z minus 1 whole square is equals to 9. So square root of 9, so it is 3. So I get 1/3 x, y, z minus 1. Now I need to calculate what is f dot n. Well, I know my expression of f. F is given by x, y, z minus 1. So f dot n is x, y, z minus 1 dot n. which is 1/3, so that comes out x, y, z minus 1. So again I get x square plus y square plus z minus 1 whole square divided by 3. But x, y, z are point on the surface, so this numerator is actually 9, so it is 9 by 3, so it is equals to 3. Okay. So the function, now the integral on the boundary, if I look at the picture again, this boundary actually consisting of two curves, two surfaces. One surface is the part of the hemisphere and the other surface is the plane z equals to 1. Okay. So the boundary integral now has two components. So first one I call S2 and this one I call S1. So S1 is the plane z equals to 1 and S2 is the hemisphere. So first I will like to calculate what is double integral over S2 f dot n d sigma. Okay. So this then double integral over S2 f dot n is anyway 3, and then I can try to calculate what is d sigma. Now for d sigma what I do is upper hemisphere can be thought of as, so I will write it as 1 plus fx square plus fy square. I will tell you shortly what I mean by f dx dy. So what is f? Well, the upper hemisphere can actually be thought as graph of a function, because I can write it as z minus 1 equals to square root of 9 minus x square minus y square. Okay. So z equals to 9 minus x square minus y square plus 1. Okay. So my fxy actually is square root of 9 minus x square minus y square plus 1. So what is fx? That means I have to differentiate. So it is minus twice x divided by twice square root of 9 minus x square minus y square. That is minus x divided by square root of 9 minus x square minus y square. Similarly is fy, that is minus y divided by square root of 9 minus x square minus y square. Then what is square root of 1 plus fx square plus fy square? This is square root of 1 plus x square divided by 9 minus x square minus y square plus y square divided by 9 minus x square minus y square. If I calculate this whole quantity, what I get is square root of 9 minus x square minus y square plus x square plus y square divided by 9 minus x square minus y square. So which is nothing but 3 by square root of 9 minus x square minus y square. Okay. So the integral now I am looking at is double integral over S2 3 times, the function is 3 by 9 minus x square minus y square. So it is 3 by square root of 9 minus x square minus y square dx dy. Okay. Now I can write this in polar coordinates as 9, 0 to 2 pi, then the variation of the radius vectors 0 to 3 r dr d theta divided by square root of 9 minus r square. Okay. This integral you can easily calculate and just check that it turns out to be 54 pi. But there is an easier way of doing it, because ultimately you are interested in doing what? What is the integral I am trying to calculate? Well, the integral I am trying to calculate is double integral over S2 3 times d sigma. So let us look at it directly, that double integral over S2 3 d sigma. So if I take 3 out, what I get is double integral over S2 d sigma. Okay. But then what is d sigma? It is the surface area of the sphere of radius 3, then the half of that, because I am looking at the hemisphere. Okay. But I know already from certain of our formulas which we calculated earlier as surface area of revolution and such thing, that what exactly is the surface area of a sphere of radius r. Well, I know the formula. The formula is surface area of a sphere of radius r is actually 4 pi r square. This is the surface area of a sphere of radius r. So if I apply that formula, it is 3 times 2 pi, then r square means 3 square. So this is then 27 into 2 pi, that is 54 pi. Okay. But still one more portion of the surface is left, that is z equals to 1. So now I have to calculate what is double integral over S1 f dot n d sigma. Notice that S1 is portion of the plane z equals to 1. Okay. So on that, which function I want to evaluate? That is, what is f dot n? So in this case, first I have to calculate n. Earlier the n which I have calculated is for the hemisphere. Now it is for the case z equals to 1. But in that case, I know that n is actually equals to k, that is the outward unit normal vector. So f dot n, since I know the value of the function, is nothing but z minus 1. So I have to integrate now double integral over S1 f dot n d sigma, that is z minus 1 d sigma. But notice that d sigma is then nothing but dx dy, because S1 turns out to be this plane region when z is equals to 1. Okay. That means the integrand is anyway 0. So this integral is 0, because on S1 z is always 1. Remember the picture? My surface is this. This is z equals to 1, the plane. Okay. So the integrand is 0. So the total integral over the boundary, that is integral over S2 f dot n d sigma plus double integral over S1 f dot n d sigma, that is 54 pi. But if we recall that what exactly was the triple integral of divergence f, that also turns out to be equals to 54 pi. That means those two sides are same, and hence divergence theorem has been verified. Let us look at the following example now. It is about evaluation of certain surface integral. Let us look at this function f x y z, that is equals to twice xi plus y squared j plus z square k. And let us say S is the unit sphere. And I want to calculate integral over S f dot n d sigma. Okay. In principle, I should be able to do that. So let us try to see what comes. So what is n now? N again is given by the formula grad g by norm grad g. So that if I calculate, I would get where g x y z okay, for each point I have to calculate the normal. So locally I can think of it as a graph, so it's okay. What I get is then 2x, 2y, 2z, so this comes out to be just x, y, z. Okay. So then the integrand will turn out to be double integral over s, then f dot n is twice x squared plus y cube plus z cube, and then d sigma, which I can calculate. Now even if you calculate d sigma and put that in the integral, you would say that this integral actually turns out to be a very messy integral. It becomes very complicated to calculate that integral, because the proper parametrization you have to use so that your integral becomes much easier, and that is going to be very difficult here. Instead, suppose we invoke to the divergence theorem, because it is in that form. Actually the right hand side of the divergence theorem, which appears in the divergence theorem, is double integral over s f dot n d sigma. That is given here. So if I apply divergence theorem, this is actually going to be equal to integral over the solid sphere, which I call d, then divergence f dv. Okay, the volume integral, that is the triple integral. Now what is divergence of f? That I can very easily calculate from this given function. So what is divergence of f? That is grad dot f. This is del del x, del del y, del del z dot the function 2x, y square, z square. This then turns out to be 2 plus 2y plus 2z. Okay. That means what I need to calculate then is triple integral over d 2 times 1 plus y plus z. It is simply dx dy dz. Okay. Now this integral I want to evaluate. Now this I can write as 2 times triple integral over d dx dy dz plus 2 times y dx dy dz plus z dx dy dz. Now you can check very easily that this integral, they are very symmetric, and you can easily show that this integral is actually equal to 0. So the end result is 2 times volume of the sphere of radius 1. Okay, but sphere of radius 1, this has got the area 4 pi by 3 r square r cube, that is 1 cube here, so it is 8 pi by 3, which is actually the left hand side of the divergence theorem. That is divergence of the function, you integrate on the triple integral over the region d, what I get is 8 pi by 3. So by Gauss divergence theorem, this quantity is exactly same as this integration which I have written here, which usually is very difficult to calculate, but if you use divergence theorem of Gauss, then it becomes much easier to calculate. So this is how many surface integrals, which are usually a bit more complicated to compute, can be transformed to a triple integral by using Gauss divergence theorem, and then it might become easier to calculate. So this is what we wanted to do about generalizations of fundamental theorem of calculus. So we have done it for plane regions, which was Green's theorem. Then we have done it for curved regions, which was Stokes' theorem. Then we have done it for solid region, whose boundary then is a surface, and that is divergence theorem. So these are all about the generalizations of second fundamental theorem of calculus for all the other analogues of integrals which we have done, namely surface integral, volume integral, and the line integral.